Hi guys, today I want to present you a circuit which I found on LinkedIn, and it was probably an interview question. And the answer and the questions were: explain the principle of the circuit and what's the reason for having Q1 and Q2 in that topology, and can we replace D3 with something else? I will do also other videos about this if you like them. So I wanted to show you how you can reason what is the reason behind these circuits, and what is the process that you can use to analyze this kind of circuit here. So in my opinion, the first thing that we have to look is what we have at the input voltage. So first we have R1 and C1. As you can see, C1 is a very big capacitor and R1 is a low resistor, meaning that this point here will have exactly the same as the input voltage, but with an RC filter with a frequency of 1 over 2 pi RC. Now, consider that there can be other reasons that for to put a resistor here or to put a capacitor here, and not only to an RC filter, but also to first limit the current. Sometimes you can put a series resistor to the input voltage to limit the current, or second, you can put a capacitor C to keep the node, the voltage node, constant. So this point here must be as steady as possible, as constant as possible, so that your entire power supply will be kept constant. So in this case, my answer would be that this RC combination is given to keep this node voltage constant, and if there are any pulses load, any load variation, this capacitor will provide energy first, and so you will have a voltage as constant as possible, because this capacitor here, so this is the voltage V, this capacitor here will provide a burst of current I, because it is a very, very big capacitor. Another thing that you have to take into account when watching resistor and capacitor is their power rating, energy rating in general. A very big capacitor like this will never be able to have, for instance, 100 volts in this kind of application, because there are very, very big capacitor, okay? 4 to 7 millifarad is a very, very big capacitor, so probably this will be something like 10 volts, 24 volts, okay? Something like that. Now we move on the second part of the circuit. Here you can see that there are one diode D3 and two diodes D1 and D2. Now, what is the purpose of this? What is the purpose of this? Okay, the purpose of this diode, in my opinion, D1 and D2 gives constant reference voltage here. Constant reference voltage to the collector Q1, because a transistor, remember that a transistor, when in linear region, needs to have a proper collector voltage, VC, a proper stimulus in the base current, EB, and then the current will flow in this direction here. Now, in order to make it work, in order to make this diode work, you have to polarize this diode with a current which is flowing from the power supply. Hence, you need this resistor R2 to make the current flow into this diode here, and then we'll have a few milliamps, a very low current to give this boost of voltage and give a constant VC. So this Q1 is okay. The second applies to the resistor R3 and the diode D3. You have to give a minimum current to polarize this diode 3. D3, so let's write somewhere. So, what? So, D1 and D2 give us 10 volts, because the sum is basically 10 volts of VC, and D3 gives reference voltage to the output, because this D3 is clamped to the base of Q1. Now Q2, in order to work properly, will need a constant base current IB, and the only method to provide that is to provide the better method to provide that is to provide a constant current IC for another transistor. So namely, by doing this, pay attention that this is not a Darlington pair. The Darlington pair has the collector in common. The Darlington pair is like this. This is not the case. So this guy is using basically another transistor to give, is using another transistor to give a constant, a good reference current here, IB, which is given by the IC of the previous stage, meaning that the gain and the gain and the linearity of the system is improved. Now, since it is an NPN transistor, you will have the load. You will have the load coming from the collector part. You do remember that when I did the current source, the current source videos, when you have the NPN topology, also for the MOSFET, the load is here. Okay, and it is in this direction. When you have instead the PNP topology, it takes voltage from here, and the load is low-sided here. So, in this case, we can control the current. We can control. Let me change color. We can control the current flowing to the load here by tuning the potentiometer here. So basically, this is current voltage. This is a current let me write somewhere. This is a current controlled voltage reference circuit. Let me write somewhere. Okay. So basically you decide by tuning the potentiometer, you decide the current flowing into RL. So I think that we answered everything. Explain the principle of this circuit. What's the reason for having Q1 and Q2 in that topology? And can we replace D3 with something else? D3 can be replaced with something else. Yes, it can be replaced with, of course, if you understood everything. Since D3 gives a reference voltage, you can substitute this with a voltage divider, because here you have 10 volts. Okay, let me write it in green. Here you have 10 volts, but if you design a divider, you can still have at this point here 6.8 volts. Okay, so you can substitute D3 with something else. So more or less in 10 minutes like this, you should say analyze an analog circuit like this. Now, analog electronics is not my field. My field is more on power electronics. But sometimes you can be unlucky and you can find a circuit like this in an interview, in a job interview. Now, I hope that I give you an insight on how you can analyze this circuit. We can open LTSPICE and make this circuit immediately to verify our results. I don't know if they can ask you also to. They never ask me to do some simulation in LTSPICE in real time, but if they do, be prepared for everything. So let's put, in my opinion, here 10 volts, 10 amps, and 4.7 milli. Let's put the ground here, and let's enlarge the circuit. Whoa. The circuit like this. Okay. So now let's put everything. We have the resistor R2. If we can clone also the reference, it would be good. D1 and D2. okay, let's put okay, D1 must be a Zener voltage. Zener voltage. Let's click on type. Okay, Zener voltage. The first is 6 dot. Okay, let's pick this guy. The second guy is okay. Let me write this guy here is 5.92. Okay, the second guy is 4. 4.5 is good. Then we have R3, which is of 7.750. And we have another diode D3 in this direction here. And this is 6.8. 6.8. Okay. So we put the Chuen Chu 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 Chu, my favorite. Guys, this is my favorite transistor. It's the first on the list, and it's really my favorite transistor. And this guy here will, okay, will drive transistor Q2 BD. I hope that we can find this guy on LTSPICE. Let me check. BD, BC, BC. No, we don't have it. So let's put. In this case, it's a little bit important, you know, because you can BC, BC. No, we don't have it. We don't have it. So let me use the BC or something. Hope that it can still work. What? Okay. Then we had the load. We have the load. We have R5. Okay, let's put here like 150 ohms like this. Then we can see if it really varies. It really changes. RL. And we have 33. Okay. Okay. Another question that they can ask you, for instance, it's what happened if I put the diode, for instance, like this, on the other verse, on the other direction, so like this, rotate 150 degrees, right, like this. What would happen? Okay, this is something that they can even ask you because they want to see how you can what is your reasoning behind everything, and if you don't have any kind of I know this circuit because I already studied it. Okay, they want to know if you can really have a good reasonment. Okay, in these cases, when they try to take a semiconductor device and they say, oh, what happens if I do this? What happens if I put like this? What happens if I mirror like this? If I mirror like this? Blah 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 blah. Okay, don't panic. In my opinion, the only thing that you can do is to always go back to the roots of the device. So we said, what happens if what happens if you put the diode like this? Okay, well, let's reason all together. You know that the diode is a device that make the current pass in one direction if the voltage across it is higher than is higher than the potential barrier. So this is the anode and this is the cathode. The drop voltage VAK is 0.7, and the characteristic of the diode is like this. Yeah, the 0.7 drop, and if you want to implement the linearity, is like this, as you do remember. So if you put the diode like this, when you have to remember always that when the voltage when the voltage, sorry, I forgot. What is it? This is I, and this is V. So when the voltage, this is V. This V, of course, is always V A K. So when the voltage is when VAK is greater than 0.7, he will conduct current linearly with, of course, with this curve here, and then you have the other part, the avalanche curve here. But you don't right now. You don't really care. So this diode, since they are Zeners, if you put them on the other direction, they will actually conduct as a diode, and so they will basically become short circuits. Okay. So, and also, if they happen to mirror, if they happen to mirror some transistors, always remember the four regions of the transistor. If he acts like if it is in saturation, off, on, linear. So remember all the condition VCE greater than, etc, etc, etc. I will make another video about that. So because there are just tricks that you can easily know and easily overcome. Okay, let's go back to the circuit, and let's run the simulation for 1 millisecond. That should be enough. So let's check the voltage here. It is 10 volts. But there is a little bit less than 10 volts. Why? Because this resistor here is giving a drop voltage of this resistor here is giving a drop voltage delta V equal to R times I. So if there are 100 milliamps flowing, or 10 milliamperes flowing times 10, you will have the drop voltage V. Okay. So here we have how much? 40 milliamps. So naturally the drop voltage is like this. 140 millivolts of drop voltage given by this resistor. Okay, so now we check this voltage here. The voltage here, as we expected, is the sum of these two. Naturally there is some drop, but we don't care. Okay. We check the voltage here, and it should be 6.8. 6.8. Okay, we have 7.2. Okay, we are here. Okay, here we have less than because we are giving some currents here. We are giving just a few currents here. Why? Because this current is directly going into the base of this transistor here. So I would expect some like few microamps, like the 96 microamps. It is correct indeed. Now we have to analyze the voltage, the current flowing to the load, which is 1 milliamp. Let's modify this resistor to 400, and let's see if we can modify the current of this load here. And we actually do. We have modified the current flowing to this resistor here. Pay attention to the dissipation, because now it is very low dissipation, but we are modifying the current. Okay. Let's check the voltage across it. This is just the drop voltage. 9042 volts. And the voltage here is 5.92. I think that we covered everything. Now, to satisfy one possible curiosity, what would have happened if the Zener diode would act like this? Well, basically, in this case, you have on this side here. Let me take this. On this side here, this is the anode, this is the cathode. Okay. At this point here, you have constant 10 volts, and the cathode here is set to ground. So VA is equal to 10, VK is equal to 0. So the anode is greater than the cathode, the diode is conducting, and is basically a short. Let's see if this is true. Let's run the simulation. At this point is not a short, of course, it is 0.7. Okay. Forgive me for this abbreviation, but okay. The diode is in the conduction region, so it is a battery. Sorry about that. It is a battery of 0.7 volts. Okay. But it is not what we want. Remember that you have also to reason like this. VA is greater than VK, and so now, since we used the diode in this region here, we had this was 10 volts and this 0. Okay, so we had VA 0 volts, VK equal to 10. So VAK equal to minus 10. So basically we are not in this region of the curve, we are not here, so it is not acting like a 0.7 diode conducting, but it is acting like here, a Zener. So basically it is giving us the breakdown Zener voltage, which is 6.8, which is exactly what we want. Okay? In this case, the diode is conducting and a lot of current, not so much in this case, it is flowing. Okay, 8 milliamps. We do not want that. Okay, we do not want that. And we want to put it like this. As you can see, the current is not flowing here anymore. Okay, because I'm not giving enough voltage to make this transistor active. So the right circuit is like this. And just through 1 milliamps is going to this diode here. I think that I explained everything. I explained everything in this circuit. Let me know in the comments if I missed something. So let me know Q4. What would have happened if the diodes were reversed? Okay. Let me know in the comments if I missed something, and let me know if you appreciate this kind of videos. Okay? So I will put the question like here. Bam. Okay? Close the guy. Ah, yes, sorry. The last thing that we can say is how this filter is working. So if there is a step load, so if r equal to if time is greater than 0.5 milli, then we have 600, else we have 200. The contrary, sorry, 200 and 100 and 500. We have a resistor step load like this. I hope that I wrote the if correctly. Okay, like this. So let's see. So this is the load. As you can see, we are passing through 100 milliamps to 50 milliamps. So what happened to the voltage? The voltage is stable. Okay, now you see that it is decreasing, but trust me, it is stable because it is just zoomed. So the difference is just a very, very few millivolts. If you don't have something like this, if you don't put the capacitor, you would have a very big drop voltage from 90.85 to 90.40, meaning that you could decrease the stability of the system and everything could go wrong. So the big capacitor is also to ensure voltage that this voltage is kept constant. In order to do that, in order to confirm that, you can see the current which is given by the voltage. Okay. As you can see, okay, as you can let's put minus C1. Let me run again. Okay, this is the current. We can make this node. Let's call this node C. Let's write IC dot of VC equal to 0, so we can make the things properly. Now you can see that. Oh, it is too big. Okay, so we have to start already charge it because otherwise it's too big the capacitor. Okay. The charging time is too high, so we have to select this time to be way higher, 100 milli, and transient of 200 milli. This is kept to 0. The initial condition is kept to 0. Let's see if we can reach that. Okay, so in 200 milliseconds we can even more. Even more. Wow. So let me put 500 milli. Ah, okay, now we can see everything. Okay, when we start from 0, so the current is giving, the input voltage is giving, of course, the current needed to charge this capacitor here, because it will start, of course, from 0 at the beginning of the circuit. It will implies, or it will take 250 milliseconds to charge. Then when I give the load here, when I give the load here, as you can see, the voltage is dropping a bit. Okay, now we have the real situation. It is dropping a bit, okay, slowly. Now, naturally, it is just to provide. Naturally, this capacitor here should block just a pulse current. This is permanent. Okay, this is a load permanent. So it is normal that you have a permanent drop voltage here because you're asking a current of 56 milliamps, which result in a permanent drop voltage of 600 millivolts. So it is also important to make this kind of analysis. Remember, it is nothing difficult. It's just using the principle that the current, the capacitor is giving you current I, because it has to give you charge, and then this current flow into here will create a permanent drop voltage on this node VC here. Okay, so it is also important to use the basic equation to understand what to expect at the end of the transient like this. So after the end of the transient, we have a voltage of 90.41 in a very, very calm situation. Okay, so from 90.4 to 90.41. Another question that you can add is what would 4.5, what would have happened if R1 equal to 1? So what happens if they change this resistor? If they change this resistor, the drop voltage will be less, because the current, pay attention to this, because the current flowing is not decided by the input, is decided by the load. So the current flowing will be always the same, but that will change the drop voltage of R1. So if you put a lower resistor, the drop voltage will decrease as well, because in the equation of delta V equal to R times I is decided by the load of the last transistor here, of the RL here, okay? So the load is decided by this guy here, and the R is kept constant. So, meaning that if you change R to 1, you will... Now what kind of dissipation you have? Let us check the dissipation of this resistor. You have 36 milliwatts of dissipation. Now you change to 1 again. Let me zoom everything on what we need. Control Y. As you can see, the drop voltage is less. The dissipation is also less. So if R is equal to 1, we have 65 milliwatt of drop instead of 600 millivolts, and the dissipation is also reduced, and the dissipation is also reduced to 3.9 millivolts, and the drop voltage, as you can see, is reduced to nothing, 90.93 volts. So not only we did answer to all these questions here, but we also improved the circuit, because at the beginning of the circuit, if you do remember, we had a permanent drop voltage given by the resistor R1. So a higher resistor in this circuit here is not needed, because the capacitor will mainly provide the role of stabilizing the C voltage. I think that I explained everything to you. Let me know in the comments if you like this kind of videos where I can make some reasoning about analog circuits like this. Let me know in the comment if you like them, and let's see you in the next video.